Great to have everybody here. So last time we had a bit of problem. So we were talking about conflict serializability, and we had an issue with the fire alarm. So hope you watched my video on conflict serializability. So there are two types of serializability that we are interested in: conflict serializability as well as view serializability. So I made a video about conflict serializability after the class. So if you haven't watched that, do watch it. I mean, if you haven't watched it, I'm just going to have a recap real quick. After that, we're going to discuss view serializability, which is a relaxed version. And we're going to go through some exercises and probably an in-class quiz about concurrency control. And after that, we're going to dig into something slightly more interesting, which is multi-version concurrency control, which is what modern databases are running on. And we're going to talk about why count queries are slow and how is multi-version concurrency control are actually implemented and the expected behavior, as well as what are we expected to know about it. And so basically, this kind of wraps up our semester for the majority of the examinable content. Next Monday, we're going to, okay, still here, great. Next Monday, we're going to have, we're going to talk about the history of databases, modern databases, NoSQL databases, and after that, we're going to talk more about vector database and its relation with large language models. And on Thursday, we're going to have a revision. So we're going to walk through everything we have talked about in this term, and I'm going to specifically tell you like what part of the course is examinable, like more probably examinable, and I'm also going to give you an idea of what the final exam looks like. So hopefully you've been studying based on the, you've been preparing for the exam based on the past exam papers we give you, but on that Thursday we're going to give the exact exam structure of our exam. I'm not going to give you all the questions, I'm going to tell you like what question is about what and how we're going to prepare for it. Okay, so that's continue our discussion in serializability. So let me go back to the Venn diagram real quick. So we talked about all schedules, and a schedule is just a way of asking different transactions to interleave their operations. And so we have all different schedules, and we're interested in checking whether a schedule is serializable or not. And we talked about there are two concepts that are vital to our course, which are conflict serializability, and view serializability, and both of them are conservative tests, which means that you can see that they're sitting inside of the all serializable schedules. So there are special cases of serializable schedules, and conflict serializability is the stricter definition, and it's the more practical definition as well, and I made a video about it. I'm going to recap it real quick. After that, we're going to go through view serializability. So basically, in the exam, in the concept of exam, what we want from you is that I'll give you a schedule, and I'll ask you, hey, is this conflict serializable? And you're going to go through the process, find pairs of conflicting operations, and give me a precedent graph, and then you're going to show me whether it is conflict serializable. And after that, I'm going to ask you, is it view serializable? Is it view serializable, and why? So that's the type of questions we usually ask in past exams. So I'm just going to quickly go through. I mean, in case you didn't watch that video, I'm going to give a quick recap of what conflict serializability is. So if we really want to think about why we need concurrency, the motivation is that we are in conflict with each other all the time if we're different transactions, especially if I'm writing on something and you're writing on something as well, especially when we're modifying things together. So conflict serializability gets the motivation from that, and then it only looks at the pairs of operations that are in conflict with each other. So the definition is that if two operations are from different transactions, second, if they're operating on the same data item, third, one of them is right, then they're in conflict with each other. So it makes sense because in order to be in conflict with anybody, they need to be from different transactions. So if I'm performing write and then read and then write again, I'm not in conflict with myself. I'm always in conflict with some other transaction. And also, we need to be talking about the same data item. If I'm doing something on X, you're doing something on Y, you don't concern me because we're not in conflict. And the only two operations that can be in conflict are the ones where one of them is right. So, which means that there are there are three types of combinations if you think about it: 2 writes, 2 read, 1 write, and 1 read. So if you both reading on the data item, you're not doing anything, we can allow like 1 million people to look at the same thing without changing it. So only in that case, we don't have a conflict. If one of the person tries to modify it and other people are reading it, then there's a conflict. So whenever we have so for instance, I'm just going to look at this example here. So for instance, our read X in transaction 1 and read X in transaction 2, they're fine. They're both reading and they're not in conflict with each other, although they're from 2 different transactions and they're operating on the same data item. And however, if you look at read X and write X from different transactions, then it means that they're in conflict. They're conflicting transactions, and conflict serializability says that for every pair of conflicting operations, we want to keep that order, which means that however you rearrange the schedules, we still want read X in T1 to precede write X in T2. So we want to preserve that precedence of conflicting operations. And how do we preserve that? So we want to make a documentation of all such conflicting operations. And what is that document called? That document code is called a precedence graph. A precedence graph looks like, let me find a nice example of precedence graph. Okay, this is an example of precedence graph, and each node is a transaction, and each edge is each directed edge indicates that one transaction precedes the other transaction due to certain conflicting operations. So for instance, T1 should precede T2 here. This edge is saying that T1 precedes T2 somewhere. Where I can find that because we're 2 writes, right? We got 2 write operations, and then T1 is before T2, which means that we have to draw an edge from T1 to T2. And if you go through all of those conflicting operations, we can draw a graph like that, and then we need to check whether this graph is a DAG. So if you learned algorithms, you know that a DAG is a directed graph without a cycle. So basically, we need to check whether this directed graph has a cycle in it. If it does not have a cycle, it means that there is a way for us to rearrange these operations within each transactions such that T1, T3, and T1, T2, T3 can be arranged and equivalent to certain serial schedule. So basically, if this is a DAG and then there's no cycle, then we can have a topological ordering of these nodes, and then that topological ordering is just the serial equivalent serial schedule of these transactions. But if this graph has a cycle, it means that there's no way for us to rearrange these operations to make it equivalent to certain serial schedules. So basically, the take-home idea is that you need to check whether there's a cycle in here. So I know cycle detecting is another algorithm problem, but for the purpose of our course, like for graphs like this, you can just use your eye. I mean, I'm not going to talk about the algorithm to detect a cycle in here. And how would you do that if you have like a huge graph? Anybody remember? DFS or recursion? So basically, you could run a DFS, depth first search, from a node, and then you can check whether there is a cycle in this graph. Well, anyways, so basically in here you can see that there is a cycle. So T1 points to T2, which means that we must have T1 before T2, and then T2 before T3, but also we need T3 before T1. So that's a cycle. Whenever there's a cycle, which means that this is not conflict serializable. Yeah. Yeah, each edge is documenting the precedence relationship between two transactions. So one edge could be generated from different sources of conflicting operations. You see that in T1 and T2, you can say that so there's an edge from T1 to T2, right? You could have gotten it from in different ways, but as long as you get that edge, it's fine. So if you're saying Rx is conflicting with Wx here, then we could write T1 points to T2 because the operation in T1 precedes that operation in T2. And also there are conflicting operations.
Does it have to be operations on the side and
Pardon?
Does it have to be like a read and a write one, or does it have to be like both on X, I assume? Or?
Yeah, both on the same data item, and one of them needs to be a write to be in conflict, because if you're both reading something, then it's fine. So you could have gotten this edge from read X and write X here, or you could have gotten it from write X and write X here. So no matter if as long as you got that edge, then it's fine. And also in an exam or something like that, you probably don't need to get all of these edges. As long as you have found enough edge to create that leads to a cycle, you can stop here and say, hey, this is a cycle, and then I'm done. Let me move on to the next question. And yeah, that's basically how it's done. And you don't need to understand why. I mean, it'd be nice if you understand the algorithm behind this and why this is the case. But for the purpose of for the purpose of evaluation and assessment, if you know how to do this, then you're set. So usually we ask a follow-up question. So we usually ask you two questions. First, is it conflict serializable? And if the answer is yes, and then the second question I could be asking you, then is it view serializable? What should you say? What would you say? You just tell me yes, right? Because based on the Venn diagram, conflict serializability is in here, and then view serializability is a larger oval, larger circle. And then if you're conflict serializable, you're definitely view serializable. You can go ahead and say yes. And if you find out that there is a cycle like this, which means that it's not conflict serializable, then you need to check whether it is view serializable via definition. So we're going to go through what it means to be viewed serializable. So basically, they're both conservative tests, and they come from different motivations. View serializability is coming from the motivation that how can we design some rules so that when they're flipping these operations around, so that it is still equivalent to the certain serial schedule. Well, view serializability as the name suggests, it looks at the view of each transaction. So basically, it forces that each transaction sees the same data. And from the first operation to the last operation, if they see the same data, if they see the same data, then we can say that they are view equivalent to that schedule. And if we can find a way to prove that our schedule is view equivalent to a serial schedule, then we say that this schedule is view serializable. So how do we do that? Well, we look at 3 rules: initial read, dependent read, as well as final write. So we look at each data item, and we look at 2 schedules. And you can pretend S prime is the serial schedule. So one quick question. If we have n transactions, how many possible serial schedules are there? If we have n transactions. So serial schedule is like, let's complete all operations in T1 first, and then T2, and then T3, and then T4, and then Tn. And then if you rearrange that order, that's a different serial schedule. So if we have like n transactions, how many possible serial orders are there? N factorial, great. So basically we're looking at all, oh, it's right here. So basically we're looking at all kinds of ways to order these transactions, and each way corresponds to a serial schedule. And if we only have like 2 transactions, then you only need to check whether the schedule is equivalent to T1 then T2 or T2 then T1. Or if you have like 3 transactions, you need to check for 6 different schedules. So you can pretend one of these is a serial schedule. Let's just say that S is something that you're given, and then S prime is one serial schedule of those transactions. So let's just say that S is a schedule of 2 transactions, and then S prime, you can pretend that S prime is T1 then T2. So that's one of the serial schedules. And here we're just basically going through all data items, and then we need to check whether these tests are passed. So we need to make sure that on both schedules, the same transactions are reading the same initial value of that data item. So when this data item is read by somebody for the first time, it needs to be read by the same somebody on both schedules. So let's just say that I'm transaction 1. I read the value of X first in S. Then, in order for these 2 schedules to be view equivalent, I must also read the initial value of X in S prime schedule. So this is the initial read, and then dependent read is slightly harder to check, but basically, whenever you're reading something, whenever your transaction is reading something written by another transaction, so Tj reads X written by Tk. If that happens in this schedule, it must also happen in the other schedule. And finally, we'll have the final write. So for the same data item X, if I'm the transaction that writes on it, I'm the last transaction to write on it, and after me there could be some reads, but we don't care. If I'm the last transaction that writes on it, I must also be the last transaction to write on it on the other schedule. So if all of these are satisfied for all data items, then we can say that 2 schedules are view equivalent. And usually when we are asking you to check so usually we're asking you to check whether S is view serializable, right? And then in that case, we will set S prime to one of the serial schedules of those transactions. Let me see if we can find a great example. Okay, so first, let me look at these 3 examples, and and these are great examples because they only involve 2 transactions, which means that for each of them, there are only two possible serial schedules out there. So for the first question, we'll need to ask you, hey, is this conflict serializable? So you can look at it. So if you do this long time, you can just look at it and then you can think about, is there an edge from T1 to T2? And then you also need to think about, is there an edge from T2 to T1? So is there an edge from T1 to T2? So in order, and they're all operating on X, which is great. So T1 reads X, and then we can just scan all of the operations afterwards in T2, and then because one of them is read, so we need to look for a write in order to be in conflict. And then we found the write in the end, so there is an edge from T1 to T2. What about T2 to T1? So for write X is the last operation. It cannot precede anything. So let's look at read X in T2, and the only operation in T1 that comes after it is write on X. So read on X and write on X, the middle two, they're also in conflict with each other, which means that there's also an edge from T2 to T1. So T1 to T2, T2 to T1, that's a cycle. Cycle means not conflict serializable. But what about view serializable? Yeah. Pardon?
Does the cycle have to contain all the nodes?
No. Just like any node, any cycle is a cycle. So that's a great question. So if we have like 5 nodes and then you find a cycle between 2 nodes, then it's still a cycle. Great. And because it's not conflict serializable, because there's a cycle in the precedence graph, we need to go ahead and check whether this is view serializable by definition. So this is not conflict serializable, and then we need to check whether this is view serializable. Well, we need to go through all of the data items in here, just one X, and let's perform the first test. Okay. What are we missing? We also need to look at the serial schedule that we compare it with. So let's just say that we have a serial schedule T1 first and then T2. So in that case, we should have a write X, read X, write X, and after that, T2 performs read X, write X. And we need to check whether T1 performs the initial read. Because we need T1 to perform the initial read, we need to compare it with the serial schedule T1 first and then T2. So initial read, that is satisfied. What about dependent read? Do we have any dependent read here? Well, we're only doing blind reading, and we are also not, so dependent read only happens when you're reading something that another transaction just modified. So right now we're just reading things blindly, and then we're also writing things blindly. And also we need to perform the blind final write. So in this schedule, the final write is performed by T2, and in the serial schedule, the final write is in where? The final write also is also in T2. So basically, whenever we ask you to check this serializability, you always need to first check conflict serializability, and if it's conflict serializability, if it's conflict serializable, it's definitely view serializable. If it's not conflict serializable, you need to go ahead and check whether it is view serializable. And let me look at another example. So schedule here. So this is also pretty easy. But here we got 2 data items now. Whenever we have 2 data items, we need to build a precedence graph. We just need to check 2 edges, whether it is T1 to T2 or whether it is T2 to T1. So What do you think? So X, write X precedes read X. They're in conflict, so there is an edge from T1 to T2. And now we need to check whether there is an edge from T2 to T1. Well, for read X, no operations is after that. For read Y, the only operation in T1 after that is read. They're not in conflict, which means that there is only one edge in this precedence graph, which is from T1 to T2. And if there's only one edge, then there's no cycle, which means that everybody happy. This is a conflict serializable schedule. We can rearrange the non-conflicting operations to make it serial schedule. And because it is conflict serializable, it is also view serializable. So that's great. And this is a slightly harder example because it has three operations. So, and also this is not conflict serializable. So if it's not conflict serializable, we need to go ahead and check whether it is view serializable. So first, you need to check. So there, you can imagine there are three nodes here, and for W, for first transaction, read on X, and it precedes the other writes. So there is an edge from T1 to T2, and then T1 to T3. And also, for T2 and T3, write and write. So T2 precedes T3 as well. And also for T2 and T1, write and on X precedes write on X in T1. So there is a cycle between node 1 and node 2. So edge from node 1 to node 2, and then an edge from node 2 to node 1. So there's a cycle. Because there's a cycle, this is not conflict serializable, and we need to, and then we need to check whether this is view serializable. So how do we check whether this is view serializable? Well, because there are three transactions here, how many serial schedules we need to check in theory? I promise you I'll not ask you to check all of them in the exam, but like how many of them? 6, right? So the 6 serial schedules that you could be checking are T1, T2, T3, T1, T3, T2, and then all ordering of those things. But we need to check whether this is equivalent to that schedule, and also we know there is something called initial read test in the view serializability test. So because T1 is the transaction that reads the data item first, we definitely need T1 to precede T2 and T3 in that serial schedule we're trying to check. So, so let's just imagine we're checking this with T1, then T2, then T3. The initial read is satisfied because in both schedules, T1 is the transaction that reads the initial value of X. And second, we can check dependent read. And in these cases, all of these writes, we have a name for it. All of these writes are called, so for this write and this write, they're called blind writes because they don't read anything from X and then they just write on X directly. And there is no dependent reads in this case, so dependent read test is passed. So because there's no dependent read in here, so we cannot find a case where some transaction is reading the value of a data item written by another transaction. So dependent read test is passed, and then we can check final write. And the final value written onto X is performed by T3 in this case, and then in the serial schedule T1, T2, T3, it is also written by T3, which means that they're equivalent. So we passed initial read test, dependent read test, and the final write test, and we figured that it is they are view equivalent, which means that this is view serializable. And how do you I feel like this is I feel like I can, let me give you a better example. So let me give you a better illustration of that. So this is the schedule we need to check S, and this is the serial schedule. Okay, maybe dark mode is not a great idea in class, but we all know that a real programmer uses dark mode. Okay. So the serial schedule, what is the serial schedule that we are comparing it? So because I was doing this in my head, so I feel like I should really fill you in. So we're checking the serial schedule T1, then T2, then T3. What does the serial schedule look like? Serial schedule should look like, first we ask T1 to do its thing, right? And then we ask T2 to do its thing, and then we ask T3 to do its thing. So basically, we were comparing S schedule with S prime schedule, and both of them, you can see that initial read checked the same, performed by T1. Dependent read, none. We don't have dependent reads. And final write is performed by T3. So final write is here, performed by T3, and the same schedule, final write on X, performed by T3, which means that S is view equivalent to S prime, and S prime is a serial schedule, which means that S is a schedule that is view serializable. Okay, is there any other, let me look at if we have more examples. Let me just do this example again to check whether they're, so this is an easier example. So in the exam, I promise it will not get more complex than 3 transactions, because in 3 transactions, in theory, you will need to probably check 6 schedules. But for 4 transactions, you need to check 24, but I'm not going to do that. So you probably see 2 transactions or at most 3 transactions. So this is S. So S is the original schedule, and then S prime is one serial schedule of T1 and T2. And what is the serial schedule we can see? So there are actually two serial schedules we could be checking. We could check T1, then T2, or T2 or T1. So T1, T2, and then T2, T1, they're both, in theory, they're both worth checking. However, because we know there is a rule called, there's a task called initial read, so we started to compare it with this one. So, so basically, T1, then T2, it should look like this. So this is the schedule. So each row is a timestamp. So we're actually comparing with S to S prime. And for S prime prime, it should be like this. Okay? So basically, whenever we want to check whether S is view serializable, by default, we're asking you to compare it with each serial schedule of these transactions. And since there are only 2 transactions, there are only 2 serial schedules of these transactions. So T1 goes first or T2 goes first. And because we know that in the initial schedule, T1 performs the initial read on X, right? Which means that this is more likely to be equivalent to S than this. Because in this case, in S prime prime, we see that T2 is performing the initial read on X. So this is automatically failed. This is automatically failed because it does not pass the initial read test. So this is this is not view equivalent to S. And here we're still checking. So initial read on X, initial read on X performed by T1. right? Initial read performed by T1, initial read on X passed, and then we need to check whether there are any dependent reads, and then we need to check whether there are final writes. So for dependent read, is basically in two schedules, they need to have the same dependent read. And in the first case, in S, read always precedes those writes, which means that we don't have any dependent reads, right? Because basically T1 reads something, and then T2 reads something, and then we just start the writing process. So we don't have dependent read. And what about in this schedule? Do we have dependent read? Dependent read happens in here. So T2 is reading the value of X, and then that value of X was just written by transaction 1, which means that now there is a dependent read in S prime, but there isn't any dependent read in S, which means that failed. So failed. And final write are the same, but it's final write is passed, but is irrelevant at this point. You see that final write T2 writes on X the last, and here the same, but because dependent read failed, so we can also arrive at a conclusion that this is also not equivalent to S. Okay, so this is actually a two-step process. Two serial schedules, none of them are view equivalent to the original schedule. Hence, the original schedule is not view serializable. Okay, so this is about as hard as it can get in an exam or something like that. So, and we're only talking about one data item. So if we had a different data item like Y, then you need to perform all these checks for that data item too. And yeah, so this is an easy example. Okay, look at if we have more. Okay, I think it's a good time to have a quiz to test your knowledge. So we're going to do the quiz together. And so conflict rules, conflict serializability, we already talked about in the beginning of the class, as well as we talked about, we also talked about, I also talked about that in the video. So we're just going to look at the quiz that I prepared. Okay, that's quiz. Okay. So let me look at, so we got like 12 questions to refresh your memory. And so first, they're all fairly simple. And so if you, but I strongly encourage you to tell me what you think the answer is so that I can explain it very quickly. So first one, which of the following statement is best defines conflict serializability? And note that these questions, you need to select all that applies. So it could be single solution, could be like, it could be like multiple, could be multiple of them are correct. So first, the schedule is conflict serializable if it's equivalent to a serial schedule where conflicts are not considered. B, a schedule is conflict serializable if it can be transformed into a serial schedule by swapping non-conflicting operations. C, schedule is conflict serializable if it has the same set of read and write operations as a serial schedule. And D, schedule is conflict serializable if it produces the same final database state as some serial schedule. Well, last one sounds pretty good, but is actually defining what serializability is. So which one is it? Oh, it's just one. I think I can. A giveaway is that there's only one correct answer in this case, out of the 4. Pardon? B, yeah. And why is that? Yeah, it's a definition. Yeah, I'm sorry, I asked a stupid question. It's the definition, so don't ask me that. So it's the definition of conflict serializability. We're looking at conflicting operations, and it is called conflict serializable if it is conflict equivalent to some serial schedule. And how do we know if it's conflict serializable, conflict equivalent? We define it by looking at this swapping non-conflicting operations. So if we can get A to B by swapping non-conflicting operations, then A and B are conflict equivalent. And if B is a serial schedule, then A is conflict serializable. Okay, great. And this should be like super easy. So which one is not a conflicting pair of operations? So to write, you have about 10 seconds to answer that question. C, exactly. So whenever one of them is a write, it's a conflicting operation, and the only time it's not a conflicting operation is when you have two reads. So two people reading the same book, don't bother anybody, but if you're reading someone else's book and he's trying to change my book all the time, then I'm kind of angry. So and which one best describes the relationship between view and conflict serializability? C. So conflict serializability is stricter condition, and both of them are conservative tests. And the reason why we always need to perform the view serializability test after conflict serializability is because when it is conflict serializable, then we can tick on the view serializability as well. But if it's not conflict serializable, we need to go ahead and check whether that's view serializable, like we just did before. So we need to go through all serial schedules of the transactions and then check whether they're view equivalent to the schedule we're trying to check. Okay, this is no-brainer. So which are considered conflicts? So you can select more than one, obviously. I got to talk to the tutor. They made it way too easy. They didn't really bother putting different data items in here. So which one is considered conflicts? You can pick more than one, obviously. BCD? Yeah, so basically whatever it is that's not to read, so if you got read and then write, or write and read, write and write, then all of them are considered conflicts. So I guess there's an ambiguity here when I say then, so it means precedes. So this operation precedes the other operations. And this one could be tricky. Which statement about conflict serializability is correct? So A, in practice, we rely on swapping non-conflicting operations to check whether it is conflict serializable. B, a cycle in the precedence graph means that it is serializable. C, when it's conflict serializable, it guarantees equivalence to a serial schedule. D, all serial schedules are conflict serializable. So which one or ones should you pick? Anyone? Or you can just pick one, doesn't matter. D? Yeah, so D is the most straightforward one. If you remember that Venn diagram we provided, serial schedules, they sit in the heart of that Venn diagram, which means that serial schedules are definitely serializable. So serial schedules are definitely conflict serializable, and they're definitely view serializable, and they're definitely serializable. So serial schedules are what we trying to get the other schedules to be like. So they need to have the same. We want a schedule to have the same effect on the database as certain serial schedules. But obviously, concurrent schedules are much faster, and that's why we study serializability. And so D is one of the answers. What about the other answer? C. So conflict serializability guarantees guarantees equivalence to a serial schedule. That's basically baked in the definition. So being conflict serializable means that you are conflict equivalent to a serial schedule. And the reason why A looks very tempting because, just like she said, this is kind of like the definition of conflict serializability. And the reason why A is wrong is because it says that we're depending on swapping non-conflicting or conflicting operations to check for conflict serializability. So we just showed that we don't depend on these swaps. We depend on building the presence graph, which is faster. Because if you try to swap them around, there are too many ways to do that, and that's not a very efficient way to check for conflict serializability. And a cycle in the presence graph is the opposite. It means it's not conflict serializable. And question 6, which statement about presence graphs are correct? So again, you could have like more than one answer. So nodes represent transactions, A. B, edges represent ordering constraints due to conflicts. C, cycle means not conflict serializable. D, a cycle guarantees view serializability. So which ones do you think are correct? Let me think about it. I mean, there are some fairly obvious ones, and so which one is the most obvious ones? Well, node represents transactions. That's the obvious one. So in the precedence graph, each node represents a transaction, and edges represents the ordering constraints due to conflicts. That's correct, because the precedence graphs are built to check whether it's conflict serializable. And a cycle means not conflict serializable. That's correct. And a cycle guarantees view serializability. Well, a cycle doesn't guarantee anything because a cycle means not conflict serializable. But if it's not conflict serializable, we don't know nothing about whether it's view serializable. So we need to check like what we did in those examples. Okay, question 7. So we have like 6 more or something. So which of the statements are incorrect? So some of these quizzes I think they're too simple, but I think that's about as hard as the parts in the exam on these lectures can get. So which statements are incorrect? So all conflict serializables are view serializable. B, all view serializable schedules are conflict serializable. Well, one of them got to be incorrect, right? And all serial schedules are conflict serializable. And view serializability is more flexible than conflict serializability. So which one is incorrect? Or which ones is incorrect? It's got to be from A and B, right? Because they're the opposite. They're the exact opposites. B. So all view are conflict serializable. That's wrong because view serializable is the bigger oval, and then conflict serializability is the one that sits inside. And if it is conflict serializability, it can imply view serializability, but not the way around. And also view serializability is more flexible than conflict serializability in the sense that there is something that we have just looked at, which is the blind writes. So if we have many transactions and they're performing blind writes in the end, which means that they're not looking at the data, they're not reading from the value anymore, they're just writing on the data item, then more often than not, because we have interleaved the blind writes in the end, more often than not, that is not conflict serializable because those write operations will be in conflict with each other, and then that will create a cycle. However, these operations they don't really create a problem to make it when it comes to making it equivalent to a serial schedule, and those are the kind of schedules that are tolerated or accepted by view serializability. So you can think about the difference between conflict serializability and view serializability to be the schedules that does blind writes in the end. And okay, this is the slightly harder one. You got to really think about this. So this is a schedule, and we have like 2 transactions, 2 data items, and which statements are correct. So is there a conflict on X or is there a conflict on Y? Is there a conflict? The precedence graph has no cycle, and schedule is not conflict serializable. I guess you have to use a pen and paper to do this, but we're just going to do it in our head. Let's just look at each data item at a time. So we immediately see write X over here. So there is an edge from T1 to T2. What about can we spot an edge from T2 to T1? No, because for those operations we can ignore them because we don't have like following operations from T1 such that we can precede them, so we can ignore them. So the only thing that worth talking about is read on X, and after that T1 does not do anything about X anymore. So there is no conflicting operations such that the preceding one is from T2, which means that there is only one edge in the precedence graph, which is from T1 to T2. So this graph does not have a cycle because this is only one edge, and it is definitely conflict serializable because there's no cycle, and there is a conflict on X created by write X and write X, and do we have a conflict on Y? Do we have a conflict on Y? Yes, and what like? Yeah. So read on T1 and write on T2. So nice catch. So read Y first and then T2, write on Y. So that's another reason. So these are one of the reasons why there's an edge from T1 to T2. Or if you can look at Y, that's another reason why there is an edge from T1 to T2. So sometimes the edge could be created from different reasons, but as long as you create an edge, you can go ahead and check whether it's conflict serializable. Okay, we're going to take a break for 10 minutes, and we're going to finish up the rest of the 4 quiz questions, and after that, we're going to talk about multi-version concurrency control. Okay, let's come back to the lecture, and let's just first finish up those 4, excuse me, hello, do you have a question? So we're going to finish up the last 4 quizzes, and then we're going to have a demonstration about multi-version concurrency control. So let's look at whether this is conflict serializable. So first, we need to check whether there's a conflict on X. Is there conflict on X? Well, we have all kinds of conflicts on X, so I guess that's not debatable. You got read and write, read and write, and all kinds of stuff. And this is actually a tricky one. Can you answer this question without making the precedence graph? Like, by definition, can you answer this question without, yeah. Yeah, so, what'd you say? Yeah, it's already a serial schedule, so you don't have to go through the trouble of building a precedence graph and then check whether there is a cycle in that. This is already a serial schedule, so T1 and then T2. So because this is serial schedule is the innermost of the Venn diagram. It's definitely conflict serializable, and because it's conflict serializable, it definitely does not have a cycle. And yeah, so ABC. So that is like a trick. So this is kind of the same. So this is also serial schedule, and this is what we call a blind write. So for T1, it reads something and then writes something, and for T2, it doesn't read anything, and then it just modifies that data item. So T2 performs a blind write here. And is this schedule conflict serializable? Yeah, this is already a serial schedule. So serial schedule implies conflict serializable schedules. So is this view serializable? Well, serial schedule implies conflict serializability, implies view serializability. So A, B, and D are correct. So the only thing not incorrect is C. So I think this is a no-brainer. So what statements about conflicts are incorrect? Conflicts occur on the same data item. That sounds correct to me. Both operations must be right to be in conflict. At least one operation must be right to be conflict. And D, conflicts create ordering constraints in precedence graph. So which one is incorrect? B, yeah. We don't need both of them to be right in order to be conflict. As long as one of them is right, then it's conflict. So if both of them are read, there's no conflict. Read and write, conflict. Write and write, conflict. Then the last one, which statement is correct? View serializability considers read from relationships. Final write must match in equivalent schedules. So obviously this is a quiz about view serializability. And the operation orders must be identical, and view serializability allows some schedules rejected by conflict serializability. So which one is correct? I feel like the questions could be framed more clearly. So D is definitely correct. View serializability allows certain schedules to be rejected by conflict serializability, and that's the reason we need to perform the check further. And actually A and B are correct. A and B are correct as well. So final writes needs to match, and initial read must to match as well. Okay, so that's a nice review of serializability. And if you did well in those quizzes, you understand everything we're talking about. So if you understand everything we talked about today in the quiz, as well as in the example, you'll be fine in the exam for that part. And now let's talk more about concurrency control. So far we have talked about like 2 serializability tests, and how do we actually use them? Well, in practice, the most widely used test is the conflict serializability test. As you can imagine, it is much faster than the view serializability test, because in view serializability test, we need to check at most, in the worst case scenario, we need to check n factorial schedule. So when we only have like 2 or 3 transactions, that's fine. That's like 2 or 6 schedules to check. But in practice, when we have like a huge database, we could have like 1 million transactions operating on the table simultaneously, and then it's impossible for us to check that with 1 million factorial schedules. So in practice, we usually use conflict serializability as the conservative test, and when it passes that test, we can go ahead and apply some locking on those data items. And there is a famous locking mechanism called two-phase locking, where we can apply locks in the growing phase, and then we can release locks in the releasing phase. And then that will guarantee conflict serializability, and that also gives you a schedule to work with. And but the thing with log-based mechanism is that log-based mechanism basically kind of works against the idea of concurrency control anyways, because the beauty about concurrency control is, so we want to design a protocol under which different transactions can run without interfering with each other. So if we always obtain logs on stuff, it's going to slow the process down. So you need to know there are different types of logs. You can log a single data item, you can log the table, or you can log the whole database. So depending on what you want from, and depending on your need, you can obtain logs of different granularities. And of course, if you obtain a huge log, it's going to block many other transactions from other users. So which brings us to what most modern databases are using. They're still using the log-based method, but they're also using something called multi-version concurrency control. So multi-version concurrency control is basically a version control mechanism in modern databases, especially in PostgreSQL. And it's kind of like, I would say, it's kind of like Git. Git is a version control mechanism for managing our code, but MVCC is designed so that it can cater to millions of users who are trying to modify the same table. And to understand MVCC, we can motivate our discussion by first looking at why certain queries are slow, and there's a reason it is slow. So count queries are super slow, notoriously slow, and we have already talked about PostgreSQL engines are optimized for so many years, for like 30, 40 years at least. And why haven't they made count queries faster? Well, there's a reason for it, and the reason is actually multi-version concurrency control. So we're going to show you the account query, and then we're going to show you the query execution plan, and then we'll come back to why MVCC is important. So let's just create this giant table first. So I'm going to create this table with about 100K rows. So it's not a huge table, but it's large enough. Create this table, and so let's make timing on. So the reason why I have 2 windows open here, because later on we're going to see how multi-version concurrency control affect different users' view of the database. So let's make timing on. So if I want to count the number of rows in here, what can we do? So now, so I'm lazy, so I'm not going to write this code. So we can pass in here. So after you turn timing on, it will give you the running time of each query. So this running time is like 4 milliseconds. This is all right, because we only had like 100K rows. But let me look at that's. But if you're looking at like 1 billion rows or like 20 million rows, it's going to significantly slow down. And if you look at the explain that we talked about, explain basically gives us a query execution plan to do it. So what explain is saying that explain is saying, hey, we're performing a sequential scan on the whole table, and then we're basically adding the counter up to get that one result. And then it also estimates the number of rows it will visit during this scan. So it takes significantly less time. And the beautiful thing about explain is that explain actually takes advantage of some table statistics stored in the database to have an accurate estimate. And in this case, if you look at it, you can see that it gives you a good estimate of the number of rows already. So sometimes they line up exactly, and sometimes they don't agree with each other, but they agree with each other mostly. So what I'm trying to get at is that the reason why this is so much slower than this is because it is actually performing the scan on the whole table. And what explain does is that it will do a sample, it will grab a sample of the database, and then it will estimate how many rows it will encounter. And in this specific case, they happen to be the same. So sometimes you can expect to see like maybe add 10 or minus 10. So you can treat explain count star as an approximate query. So in real life, when people want to know the length of a really long table, they don't bother running this query, because in our case it takes 4 milliseconds, but maybe for Facebook's case it will take a few minutes, and it doesn't help them to get like an exact count to understand the table. Most likely, when we want to have the count query, we want to have a rough idea of how many tuples are there, like how big the table is. So what they usually do is that they do explain, and then it will give you a fairly good estimate of how many tuples are in the table. But it still doesn't answer the question why it is so slow. So we only said it is so slow is because it needs to scan every tuple in the row. But that is one of the reasons it is slow. The other reason why this is so slow is because of MVCC. So if we look it up, there is a page dedicated to explaining why counting is slow in PostgreSQL Wiki. It says that, so this is something I'm going to read, and I don't expect you to like all of a sudden understand that after reading this sentence. So different transactions can see different row versions. So there's no single catch table size for everyone. And if you want to get the number of tables from your transaction, you must visit all candidate rows and apply visibility. And that's usually a sequential scan over the whole heap. So what it means is that PostgreSQL, the reason why we have a PostgreSQL server is because it allows millions of people to use that. And when millions of people are using that, different people have a different transaction ID. So you have your transaction, I have my transaction. And it gives different transaction different view of the table, so that there is no correct answer of how big is the table. It depends on where you ask the question. So underneath the SQL engine, it is forced to do a sequential scan on the table, on the whole table, to get that exact count for your transaction. So, so here we're going to officially talk about a multi-version concurrency control. So multi-version concurrency control is a way that provides consistent versions of the data by basically creating different versions of the tuple for different users. So that, and in this way, we can reduce the log contention by keeping more than one row versions. So basically, if two people are trying to modify one row, in the locking-based method, I need to obtain a lock, and then I'm locking this. Nobody else can mess with my row, and then I change my row, and then I release the lock, and then somebody else can do that. Well, that reduces concurrency because we could have been working on different versions of the rows, and my rights shouldn't be able to block other people's rights in theory. So that's what my multi-version concurrency control is doing. So the main idea is that for each row, we keep the version number of the row. So basically, if we think about the 4 fundamental operations, what are the 4 fundamental operations in database? So we got insert, delete, update, and query. So when you're inserting something, right? So when you have a table, when you insert a row, you just insert a row in multi-version concurrency control. And when you delete a tuple, what do? We just change the version number on that row so that the most updated transaction will know that this cell is dead. So there's a difference between a live row and a dead row on the multi-version concurrency control. And when we insert something, we insert a new live row, and when we delete something, we mark the live row as dead. So we don't actually remove this row, we just mark it as dead. And when we update something, we do a combination. We just insert a new row, and then we just mark the older version as dead. So basically, update is a combination of insert and delete. And what about query? What if I want to see the table, what the table looks like? So who is going to determine what rows are visible to me? Well, it depends on what transaction I'm sitting in. So if I open up a transaction, I'm sitting right here. My transaction number could be 100. And this row, they have 2 transaction numbers associated with each row, which is the minimum transaction number and the maximum transaction number. The minimum transaction number is the transaction number that creates it, and the maximum transaction number is the one that deletes it. So if my transaction number is between those 2, then I can see those rows. But if my transaction number is less than the minimum transaction number, which means that I'm viewing the older version of the database. So basically, if I'm looking at the version 100, and my version is 100, and some other transaction are inserted a new row or updated the value of my row in version 120, then I cannot see that change because my version number is way lower. But if my version number is higher, my version number is like 130, and then the version number of that row is between 120 and 130, then 120 and 140, then I can view that row. So that's the whole idea of multi-version concurrency control. We just, instead of actually changing the values, the tuples in the physical table, we always add tuples. We always add tuples in the end, and when the tuple is outdated, we mark it as outdated. Let's look at something let's look at it in action. So this is a example that we've been looking at for so long. So this is bank transfer example. So this is a simplified version, of course. So we're going to have account table, and each people we store how much money they got. So right now, okay. And in order to demonstrate the multi-version concurrency control, you need to have 2 users. So on the left-hand side, we have a user. On the right-hand side, we have a user as well. So I'm going to attach to MVCC. So let's create those tables. And I'm going to turn timing off. Okay, timing is off. And so we're going to run this query from both sides. So we're going to check how much money Alice have. So from both sides, Alice have $1,000. And if we check accounts, Alice have 1,000 and Bob has 500. So let me make it slightly larger. Okay. And one thing, if you want to make sure that So everything, we have already know that everything in SQL that ends with a semicolon will be automatically wrapped into a transaction, right? If you don't do anything, if you just do that, it is considered a transaction. But if you want to do multiple steps and wrap it up as a transaction, you need to use begin and commit. So now I begin my operations. So right here, I begin my operations. And here on the right-hand side, I also begin my operations. So they started two different transactions. And now I'm trying to change the values for Alice and Bob, and I'm going to see whether the person on the right can see the difference. So let's just say that I want Alice to transfer $100 to Bob. So if I do update, okay, I'm just going to copy and paste. So I'm going to say for Alice, let me just transfer $200. So I'm going to set Alice's balance to to 800 and to 800, and if you do that, on the right-hand side, we can see that Alice's balance has changed. But because we haven't committed yet, on the left-hand side, Alice's balance is still 1,000. And now we have deducted $200 from Alice. We need to pay that to Bob. So we need to change this to, okay, this name is Bob. And then, so Bob now should have like $700. So $700, and then if you check it on the right-hand side, on the bank side, the transaction has been made, but we haven't committed yet. And on the left-hand side, on another user's side, we have nothing has changed yet. So this is pretty cool because as long as we haven't committed on the right-hand side, all of these operations are not in effect. So if we do have commit, if you do commit, all of these changes are committed to the database, and now if you see from another user's point of view, the changes have been updated. Okay? So, so basically, this is a demonstration of we are giving different users different views based on what transaction number they are on. So right now, we haven't shown you the transaction number associated with these two people, but we have only shown you that the bank and another user, they have different view of the database, and those views are isolated from each other. So isolation is one of the property of transactions, ACID. So isolation means you need to make sure that users have isolated views of the database, and their operations are also isolated from each other. So this is, and let's look at let's look at how multi-version concurrency control actually handles it. So remember we talked about the transaction number. So we really need to look at the transaction number of those cells. So xmin and xmax are two inbuilt columns that are available for each table you create. So basically, for every table you create, they could have you could query xmin and xmax. And another useful thing that we could use is we need to select the transaction ID. Okay, so this is transaction ID. So if we look at transaction ID here, it is 63285. And on the left-hand side, this is a transaction that we created like a couple minutes ago. We haven't committed yet, right? So if you look at the transaction ID of this, it should be lower. They should be like, no, this is not lower, but it's different. So it's a different transaction ID. And I just commit both of them. Okay. Let me just commit both of them. Now that both transactions are Now that both transactions are committed, let's look at the table again. The table is 800, 700, great. And let's look at 800, 700. And now let's look at, let's select name and balance, as well as the minimum transaction number and the maximum transaction number. So X min and X max. So basically, X min is the transaction that created those rows, and X max are the transaction that delete those rows. So basically, these rows are updated by transaction 63284, and maximum transaction ID of 0 means that this tuple is currently alive. So this tuple is currently alive. Let's look at on the other side. It should have the same, right? And now let's start a different transaction. Let's begin a different transaction here. And now let's also begin a different transaction. Yeah. And if we look at this, this is the same, but let's look at the transaction number of those two users. So now they have different transaction numbers. And obviously, because we started the transaction on the right-hand side later, it has a slightly larger transaction number. And so we're going to make some, so on the left-hand side, it is still looking at this version of the data. So we're seeing that these tuples are created by this old transaction, and these tuples are alive, right? Now, what if I change these values again? So if I change Alice, if I change Bob, I change the money to be maybe 100. If I change Bob to 100, and if I change Alice to 200, so which are way lower. And if I, this is still the same, and if I change those numbers here, and if I check these balances as well as minimum and maximum transaction number on the right-hand side, I'll see that now, we see that the minimum transaction number has changed from 284 to 288. So which means that these two tuples have been deleted, and these two tuples are the new live tuples. And if you look at from here, you see that this is the interesting part. On the left-hand side, these people are still looking at the balance and the name are not changed. So because the right-hand side, because on the left-hand side, it is still in the transaction 632. It is in the transaction 63287. So that is why we're still viewing the older version of the data, which is 800 and 700. But it knows that this data has been updated. So it knows that, hey, we're viewing the consistent data of our snapshot. However, we also know that these tuples have been updated by this transaction. So this transaction is basically the transaction on the right-hand side. So basically, we're saying that Alice has $800, Bob has $700, but these data are outdated and they are already deleted by transaction 63288. So yeah, and if whatever you do on the right hand, and if you commit those changes and then you check them again, you'll see that. So let me see that. So on the right hand side is that, and then I'm just committed. Okay, and if we commit it, we can see that this is the most updated row. Bob has $100, Alice has $200. And then a live, this is the characteristic of a live row, a live tuple. A live tuple has a minimum transaction ID, so which is the transaction ID that created those rows. And then the maximum transaction ID is set to 0, which means that these rows are not dead yet. So this means that these rows are alive. And in here, it means that these rows are already dead. So if we get out of this transaction on the left-hand side, commit, God. And then if we run it again, you can see that, let me get the transaction number. Now the transaction number is 289, which means that we are in the later version of the database. And if we run this again, we should be able to see these updated values of 100 and 200, and we can see the same thing from both sides. So, so that's a pretty interesting phenomenon, from my opinion, because in this way, what you're doing is that you're always creating new rows in the database, and instead of locking the rows to allow different transactions to modify the data, you ask different transactions to modify different places of the data. So basically, they're creating different row, and then we then stamp a different version number on it. And the thing is that if we keep doing this, the table will get longer and longer and longer, right? So the table gets longer and longer and longer. So do you think that's a problem? So that's a very important question. If we keep doing this, so whenever we insert something, we insert a tuple. That's fine. Whenever we update something, we keep the old tuple and we also insert a new tuple with a new version name. But if we always do update like this, the table will get huge, right? Because we have some legacy old data sitting in there, and then the version numbers are way small and not relevant to our current transaction, and then our table just grows larger and larger. And what do you think we should do in this case? And what do you think they're doing it? Yeah, it will record all of the big versions behind, like from version 1 to version 200, and all of the tuples are still there, like version 0, 100, and version 2, and then all the way up to version 200. And if we have more versions, table just gets longer and longer and longer and longer. And at one point, you don't have enough. Either you don't have enough disk, or the transaction number. You remember, transaction number is an integer. The transaction number gets overflown, like integer overflow. So what should we do to clean it up? Mm-hmm. Get rid of the old versions. Yeah, and brilliant. But question is, how do we at what manner are we getting rid of the older versions? Like if we have now the table has grown to be 1,000 rows, let's say. 1,000 rows, and then 100 rows of these 1,000 rows are actually updated, are the most updated data. And then which means that 900 rows in here are outdated data. And how do you remove the old data? So there's a keyword, there's a command you can do. You can vacuum, so it will get rid of all of the old data. But how does it get rid of it? How do you think it will get rid of it? In the spirit of multi-version concurrency control. So if we got, let's say that you have 1,000 rows, and then 100 rows are legitimate rows, and 900 rows are legacy rows. So do you just remove all of that and move that to top? Or do you just scratch those things and then make holes in the database? So what do you think should happen, and what do you think is happening? So think about what happens. What happens? Like let's just say that you have an array, right? Array with 100 items, and among these 100 items, 10 items are what you want. What do you want to? How do you want to get rid of all the other 90 items? If you have an array of size 100. Well, you want to modify things in place because obviously we don't want to always create a new array and then move things into the new array. So we want to modify things in place. So that's all we got, like 100 entries. And if we're talking about array, what we really do is that we just scratch all of those, we just get rid of all of those legacy tuple, and we just move everything to the front, right? We just move that we just move that 10 rows to the front, and then we adjust, maybe in C++ we can do that, and then we can adjust the length of the array, and then we can just only keep the good part, and then we just get rid of the old part. However, that's not how it's done in multi-version concurrency control, and the reason is because it is super slow and is a waste of space. Because when you try to scan the whole table and you want to identify, you want to grab all of the updated tuples and move that to the front and then adjust the length of the table, that doesn't work well because the time complexity is too high, right? You have to move things around and then the time complexity is too high. What is happening here is that they will just scratch them. So you have like 1,000 tuples, they will just scratch the data on the 900 legacy rows. They'll just scratch them, and then they will just leave the 100 good data in there. And then the database now is like 1,000 rows with good row in here, good row in here, good row in here, 100 good rows here and there. And we're left with 900 holes. And the beauty about having 900 hosts is in the future, let's just say that you're now started to modify things again, you can basically, you don't have to append things in the end now. You can just find a hole that you just scratched and then reuse that space. So that's what vacuum is doing. Vacuum is periodically getting rid of the old tuples, and it's not moving all of the live tuples together to the front like we do in arrays. It basically scratches all of the legacy tuples, and then this legacy tuple space can be reused in the future. So if you do like another insert, it does not make the table longer. It will just find the first hole, and then it will put it in there. And then if you do another update, it will just make this row outdated, and then it will find the second hole, and then it will insert that data over there. So that's how vacuum is running periodically, and that's pretty much everything we need to cover for multi-version concurrency control. And the only thing that could be tricky is about these version numbers. So whenever you, let me demonstrate the version numbers again. So what this does is that it will return the transaction number associated with this transaction. So if you are always running this, you can see that this number gets larger and larger and larger. This is because every SQL statement like that, so this select statement itself is a transaction. So that's why the transaction numbers keep changing. And what actually decides your view of the database? Well, if you start like we did before, if we start a begin here, everything after this is a transaction. And if you check the transaction number here, it still stays the same because you haven't committed yet. And in this transaction, it will always look at all of the tuples where the minimum transaction ID is lower than my transaction ID, and also the maximum transaction ID is larger than my transaction ID. So that's what determines what you see. So basically, your version number determines what you see, and different transactions has different transaction numbers, and that's why they are seeing different views of the database. Okay, yeah, that's pretty much it. And So basically, the vacuum is run every now and then to prevent the transaction number to be integer overflown and to prevent the legacy tuples taking too much space. Yeah. Go back to here.
Why the current transaction number is larger than the old one? Is that like just equal to?
You mean they're always equal? And on the right-hand side is always changing, right? Is that your question?
No, the question is why the current one is larger than the.
So the current one, you mean the right-hand side?
Why it isn't equal to the old one?
Oh, you mean the right-hand side? Oh, because on the right-hand side, we didn't start the transaction by saying begin. So on the right-hand side, every time you run this is a different transaction. So every time you run this is a different transaction, and then we have a different transaction number on it. So every time you run this select stuff, it is you can imagine there's an invisible begin and commit wrapped around it. So every time you run this is a transaction. But in here, this is still within the same transaction. That's why the transaction ID doesn't change. Does that answer your question? Yeah. So that's the reason why when we made modification on the right-hand side, the left-hand side sees the same data. So even if we change everything on the right-hand side and the data is now updated to be like 500, 700, the left-hand side still sees the same data. And that's why, because the left-hand side stays in the past. So here we're staying in the past, so that's why we can only see the past version of the data. Unless we commit our current transaction, and then now we can see the updated, data again, and also basically it will see the updated data. And yeah, left-hand side. It just keeps changing. That's it. Yeah, it just keeps changing. It's everything is wrapped in the transaction. So yeah, and one last question. Maybe I'll prepare more next time. So what is the So how does multi-version concurrency control primarily improve concurrency and serializability in PostgreSQL? So A, it uses a single global log on the database for every transaction. Second, it allows readers to not block writers and writers to not block readers. So basically, people not getting in the way with people. C uses a single immutable version of the database for transactions. D, it strictly enforces a total ordering of the transactions to prevent conflicts. Which one should it be? I feel like this is too easy because I feel like even if you don't know anything about multi-version concurrency control, you can at least get rid of one of these questions, which is pretty dumb. Like C, it says it uses a single immutable version of the database for all transactions. I mean, we're talking about multi-version concurrency control here, and you're talking about single version, so that's definitely incorrect. And so what's the correct one then? B. Yeah, so the beautiful thing about multi-version concurrency control is that it reduces the use of logs, and of course it does not use a single global log, and it does not enforce a total ordering of the transaction to prevent conflicts. So B is the correct thing, so it allows readers and writers to not block each other, so every transaction can do its own thing in its own version. And after they commit, they can see the most updated version. But when they're in their old version, they can only see what they're allowed to see. Okay, that's which brings us back to our question: why is const query so slow? Now you understand why. The first reason is that every people have different view of the count queries. So you're kind of forced to do a sequential scan, because you need to go through every row and check whether your version number is between the min and max. So there's no easy way to do it. You have to check it. And second of all, in a giant table, maybe only like 50% or maybe there is like 40% of the tuples are updated or relevant to your transaction number because there are many holes on the database. So eventually the time complexity of counting this could be even larger than the result size, if you know what I mean. So let's say that your result size is like 100 rows, but in the actual table, it has like 300 rows because there are legacy tuples. So you ended up scanning 300 rows to get the count of 100. So that's why count queries is so slow. So I mean, they cannot really make it faster because we need multi-version concurrency control. This is much more important than obtaining accurate count queries. And if you really want, like for analysis purpose, you can basically get away with using explain count select. So that will give you an estimate via sampling. Okay, so that's it for today, and have a good weekend. So next week, we're going to talk about modern database and vector database, and then we're going to do a revision and review the exam structure.
For this question, I'll just put it over there. Yeah, sure. If we use the field as of this one, which as is called?
If it's not complex serializable, you can go ahead and say it's no. If it's not complex serializable, which means that you're not in a small circle, but you still need to check because view serializability is like allows more scanning. So you still have to check.
Okay.
But if it's like yes, and then
This must be yes.
yeah.
So why this is not yes? Which has this?
I think we demonstrated. I think it's dependent read.
Why is that? I'm not quite sure why it's read. Kind of read this fact.
So here, there's no dependent read in this case. But if you look at the serial schedule, which is Rx, Wx, and then followed by Rx, Wx. So R2 is reading that, but in this case, it's not reading that. So that's why they have. So right now, our T2 is reading something, basically the same thing, right?
Yes.
But in that serial schedule, you're reading something that he wrote.
Row from T1.
Yeah, from T1. So that's different. So that's why different dependent read is fair.
So for the definition of dependent read, is it happen at the same transcription or happen at the
Different transaction. So you have to read something another transaction wrote. Then that's a dependent read across transactions.
And two schema must be same to be read.
But data item must be same, yes. Yeah. So for each data item, we check initial read, dependent read, and final write. So now we might only have X, so we just check for X. If we have Y, then we can perform that for Y again.
And also for the initialized read, is it just check the first value of the every schedule, every transaction?
You need to check whether that transaction is performing the first read on that data item. So here, T1 is performing the read on X, which is great, and then in that serial schedule, T1 is also performing, so that's fine.
I mean, what if we have multiple values? You mean
Yeah, check everybody. So every data item we perform those 3 checks. So let's just say that in here T1 performs the initial read. T2 performs the initial read on Y because it reads before that, right?
Yes.
And then T2 actually performs the initial read on X because T1 is not reading on X. So T2. So that's how you check.
And the serial schedule must be saved.
You got to check for all serial schedules, but obviously you can get rid of a lot of serial schedules just by looking at initial read because you got to start with T1, right?
Yes.
T1 reads first. So you only talk about you look at the serial schedule starting with T1. And maybe so now because it's 2, so T1 then T2. But if you have like 3, then you need to check T1 first definitely, and then you need to check T2 to 3 or T3 to 2.
Yeah.
So that's the only two possible serial schedules.
I have this question, how do you submit the assignment because it doesn't mention anything?